Yeah, I totally care. So, really quickly, we looked at orbits last day, and we said the key idea is this. When you're in orbit, gravity is pulling you in a circle. I wrote this equation for orbital speed, but I said, don't memorize that. Instead, what you want to memorize is gravity, what's pulling you in a circle. Gravity is what's pulling you in a circle. We looked at a neat orbital simulator, which gave us all the various permutations and options that are out there. The universe is pretty cool. We talked about how in orbit, actually you're in free fall. We said that the way the astronauts stay up there is not because they're weightless. mg is still acting on them. In fact, on the ISS, you can calculate it. G on the ISS isn't 9.8. It's about 9.3, I think, or so. It's still very close to this. They're falling. But we give them just the right tangent velocity, orbital speed, so that as they fall, they're also moving sideways at exactly the curvature of the Earth. And once again, this is why Sir Isaac Newton impressed us so much. He visualized that and wrote about it in 1580, before we even knew what outer space was. He said, I'm pretty sure this would work. Michael asked, could you do it on the Earth? We actually did calculate the orbital speed at the Earth. The orbital speed on the Earth is about 8 kilometers per second, just about. We said the issue here is air resistance. You burn up because of air friction. Where is there no air friction? Why, outer space. So we left off with example 5 here. We said, if it takes a satellite 300 minutes, and I underlined the word orbit, I said that's my trigger word, that's what tells me if I'm in orbit, gravity equals Fc, then how high is it above the Earth? Now, we found the orbital radius. Ooh, we ended up doing a little cube root, which was kind of cool. We found the orbital radius, and then to get the altitude, we said, oh, the altitude is going to be the radius of orbit minus the radius of the Earth. That's going to equal the altitude. Hey, what's the satellite's orbital velocity? Okay. Sammy, can you read to me part B again, please? Did you say orbital? We're in orbit. You know what? That must mean that gravity... Come on, let's try this again, colors. Here we go. That must mean that gravity is pulling me in a circle. Again, I had one kid one year try and memorize every possible permutation and outcome. Ashley, what I'm saying is, look, as soon as they tell you you're in orbit, we can start there. And then we can say, I know that gravity is big G, big M, little m over r squared. That's the same one we used in Physics 11, except we said we're going to go big M for planet, little m for orbiting body, and we'll use r because it is moving in a circle, equals m. Which acceleration equation, centripetal acceleration equation, am I going to use? Well, what are they asking me to find? Oh, let's use the one that's got the v in it then. By the way, technically I should have asked for orbital speed because velocity would want the direction. But, well, I guess we'll say a tangent to the radius, but it depends on whereabouts in the orbit it is, right? Conveniently, again, compared to the last one, when we plugged in the period, when you plug in the period, r's don't cancel. You end up with an r cubed because one r is on top on the right-hand side and two r's are on the bottom on the left-hand side. When you plug in the orbital speed, however, one of these r's will cancel. Okay? So I just got to get the v by itself, which I almost have. I have the v squared by itself. Next step is what? We get some deep narration to this. That's okay. Square root. Big G, big M over R. Which, again, you can memorize if you want to, but meh. Let's see. This is going to be the square root of 6.67 times 10 to the negative 11. I think we're around the Earth, yes? Yep. So the mass is 5.98 times 10 to the 24th. Divided by, we are going to have to use the orbital radius from part 1. Now, normally I would try and have this answer stored on my calculator, and I would use that stored answer, but I don't know about you, I put other stuff on my calculator. So I wrote down the orbital radius was 1.48 times 10 to the 7th, 1.48 times 10 to the 7th. Orbital speed is going to be, and I think I went on my rant yesterday about how this is where you really want to be practicing the scientific notation stuff, because every year I have kids that write all the right answers and get the wrong numbers. So write all the right numbers and get the wrong answers. So don't be one of those meatheads. Figure out how your calculator works. Yep. That looks about right in that I know on the Earth's surface it's 8,000 meters a second, so I'm assuming as you go further up you don't have to go as fast. In fact, the further away you are from the Earth, the slower your orbital radius. Sorry, the slower your orbital speed. The bigger your orbital radius. Oh, and the further you are away from Earth, the longer the period. Is it, you get 5.19? Times 10 to the 3rd? Yeah. By the way, how much kinetic energy would this satellite have? Oh, you would go a half m. Did I give you the mass of the satellite in the question or not? No? Okay, let's suppose if the satellite had a mass of 1,000 times that answer squared. So one of the things, in fact, the next lesson we'll start talking about orbital potential and kinetic energy. It's a nice extension. Where would that energy come from? Rocket fuel. And as I mentioned the other day, when we launch things in orbit, when you see that huge rocket with that tiny satellite that we're launching, a lot of that fuel is not to get it up there. A lot of that fuel is once it's up there, we got to give it a lot of kinetic energy. It's got to come from somewhere. It comes from the rocket fuel. Oh, I wrote down here scalar equation. I guess this is the one that has the period in it. Okay, let's write down here gravity equals circular big G big M little m over r squared equals m 4 pi squared r over t squared. A mass cancels, and r does not. All right. Let's put two equations in this box. Let's go like this. For the first equation, let's see if we can get the t by itself. How? Where's the t on the bottom? I don't like that. Where can I move that t to? Top over here. And this r squared moves over here. And big G, big M, you know what? I think t equals 4 pi squared r cubed over big G, big M. Well, that's really t squared, so square root. The other thing we could do from that equation is we could get the radius r by itself. How? I think both those r's would move to the top. I'd have an r cubed. T squared and a 4 pi squared would move across. I think we'd get r cubed equals big G, big M, t squared over 4 pi squared, except Cliff, how to get rid of a cubed? Cube root. There. Claire, you want to memorize those? Go ahead. I got better things to memorize. I'm good at the whole stuff moves diagonally, cross multiplying. Yeah, it's a fairly complicated equation, Petra, but if you're long, be careful, be careful, be careful. But if you are, I think it's doable. It's up to you. Those are not on your formula sheet. I just got in the habit of rederiving them every time also because it's kind of good practice. Put your pencils down. Gesundheit. So let's look at a few more. Example 6. By the way, I think, and I don't think I've said it, but I would say I think for all these questions, I like these questions. I like these questions. In that, on your test, you're either going to be given the altitude or the radius and find the velocity or the period, or I'm going to give you the velocity and say find the altitude or the radius or the period, or I'm going to give you the period, I'm going to say find the velocity, the radius, or the altitude. Okay? So what word did I underline in this question here? Altitude. Just understand, first of all, part A says, what's its orbital radius? If I tell you an altitude, what I'm saying is I'm giving you that distance right there. This is 1.2 times 10 to the 6th. So part A asks, what's its orbital radius? Well, its orbital radius would be that distance, I'll call it R orb, right there. I'll be honest, on your test, I won't ask part A. I did it in the homework here to let you know, don't get altitude and radius confused. On the test, I have no problem giving you an altitude and expecting you, William, to clue in, oh, that's from the surface of the Earth. What I'm doing doesn't work from the surface of the Earth. It only works from the center of the Earth, or the moon, or Mars, or whatever planet I happen to have us orbiting around. So orbital radius is going to be radius of the Earth plus the altitude. What was the radius of the Earth? It's on your formula sheet. I can't remember. 6 point something. 6.38 times 10 to the positive 6, I think. Yes? Negative 6 would be a pretty small planet. Maybe we are, Mr. Dueck. Maybe we're actually like an atom in some other huge molecule. Isn't that why the solar systems look sort of atomic? No, it's because that atomic model that they teach you is bogus, right? You guys have learned that. That planetary model is complete garbage. Altitude is 1.2. Are they both times 10 to the 6th? Then you know what? I think it's just going to be 6.38 plus 1.2 all times 10. And you can do this on your calculator if you want. But I think it ends up being 7.58, double check me, times 10 to the 6th meters. 6 and 1 is 7. 0.38 and 0.2 at 0.58. It's all times 10 to the 6th, so the decimal points line up. There's the orbital radius. Now that I have that, again, for all of these, Claire, as long as you know one of the orbital radius, altitude, speed, or period, you can find the other three. So, in fact, I was going to say, I bet you part B is going to want the orbital speed or velocity, and part C is going to want the orbital period. So B. Josh, what did I ask you to find in part B? Did you say orbital? Gravity is what's pulling us in a circle. You know, how much room did I left you a fair bit? Okay. Let's try going, we'll do part B on the left side of the page. We'll do part C over here, and that way you can kind of see the similarities and the differences. Hey, gravity, help me out. Gravity, help me out. Sure, Peter, what's the equation that I'm going to put there? No. Equation. No number yet. No numbers yet. Gravity, what am I going to put there?
Big G.
Keep going.
Big M.
Yeah.
Little M.
Yeah. Yeah. Circular motion. Don't forget to put the mass because it's circular force, not acceleration. Little m times, hey, which A am I going to put in there, Peter, my friend?
4pi squared.
What are they asking me to find in part B? Can you read me part B? So which one? Yeah. By the way, you would be correct over here. Boy, this thing is really acting slow. I would go big G, big M, little m over r squared equals m 4 pi squared r because it did in the third one, which I called B twice, but I crossed out and made C. It asked for the period. Yes? Okay. Hey, in both of these, again, once you have the satellite up there, it's easy to keep it up there. Where the mass is not going to cancel is in the next lesson when we start looking at how much energy it takes to put stuff up there. I'm sorry, it takes way more energy to put bigger stuff up there, which is why we try and make stuff as small as possible. That's why we built the ISS in segments. We could never have built the ISS in one big fell swoop and sent it all up there. Not just the construction aspects would have been too difficult, but it would have been prohibitively expensive. You may have heard, by the way, about a space elevator. That would be a cheaper way to get stuff into orbit. We'll talk about that sometime. Oh, also in the left-hand one, but not in the right-hand one. Common mistake. Kids want to go, don't write this down, don't write this down. They want to go, cancel, cancel. No, you can't cancel a bottom on the left with a top on the right. Nuh-uh. Peter, what did you say they're asking me to find in the part B?
The orbital velocity.
Holy smokes, I got the V by itself almost already. It's going to be the square root of big G, big M over R. By the way, again, as R gets bigger, as you move further from the Earth, what happens to this answer? As the number on the bottom gets bigger, as you divide by a bigger number, what happens to your answer? You don't have to go as fast. The further the satellite is out, the less kinetic energy you got to give it. Oh, but actually, correspondingly, the more potential energy you're going to have to give it to get it up that high. Okay. It's going to be the square root of 6.67 times 10 to the negative 11. Mass of the Earth, unless I say different, assume it's the mass of the Earth, unless the question specifically mentions a different planet or astronomical body, divided by, what was the orbital radius? It was 7.58 times 10 to the 6th. What do you get? I know it's going to be less than 8,000. Not that I don't trust you, but I want to try this myself too, because I like this stuff. Square root 7254.002, that one there. So 7.25 times 10 to the third. And it's a speed, meters per second. Hey, let's solve for period over on the right-hand side. Oh yeah, this is where I'm going to move period up there, radius squared up there, and big G, big M down there. I think I'm going to get T squared equals 4 pi squared R cubed over big G, big M. How to get rid of a squared? Square root. Okay, by the way, before you start crunching numbers, as you move further from the Earth, as radius increases, what's going to happen to the orbital period? It's going to increase. And this brings us to a magical special period, one that we like. There's something called a geosynchronous orbit. A geosynchronous orbit appears to stay above the same place on the Earth at all times. If it looks like it's staying above the same place, in hours, what's its period? 24 hours. What that means is if you go 24 hours times 60 minutes times 6 seconds and you plug that in, you'll also find they all end up having to be at the same radius. All geosynchronous satellites must be at the same orbital radius. Now, thankfully, that radius is pretty far away, and that's such a huge circumference of a circle, it's not going to be crowded up there for a long, long time. But we really find that a huge advantage. All the GPS satellites, for example, I think, is there 60 GPS satellites, I think? Those are all in geosynchronous orbits. They have to be. That's It's one of the ways they know where they are on the Earth and can send stuff back to you is they're programmed to be above a certain point of the Earth. Okay. Anyways, let's crunch numbers. Nerd moment over. 4 pi squared 7.58 times 10 to the 6th cubed. I don't use that cubed very often. Divided by 6.67 times 10 to the negative 11. No, that's wrong. 7 to the 6th. That thing cube. You know what? I might need to put this in brackets. I'm going to be a little paranoid. Bracket 7.58. Scientific notation button 6th cube divided by, definitely have to put the bottom in brackets, 6.67 negative 11 times 5.98 24th. Uh-oh. Negative 11 didn't show up. Negative 11. Boy, I better double check. 4 pi squared, 7 times 0.58 times 10 to the 6th, all cubed, check. Divided by that whole mess, check. Well, oh, square root. Yeah? No, I wasn't getting the r by itself. Cube root if I was getting the r by itself. Square root getting the t by itself. By the way, you're seeing lots of room to make sloppy mistakes, right? 6.565, so 6.57 times 10 to the 3rd seconds. Just because I'm a nerd, I'm going to divide by 60. Okay, every 109 minutes. Rotates around the Earth a little less than every 2 hours. Okay. By the way, if you know that the ISS rotates around the Earth every 94 or 96 minutes, I can't remember which one, you can certainly find the orbital radius of the ISS and thereby its altitude. And did I yelled at you about installing the app last day, yes or not? Yeah. Okay, good. Homework. Number 1, we talked about it, but it's worth repeating. You can explain in your own words. 2 is good. Mr. Dueck, they didn't tell me the mass of the planet Mercury. Betcha it cancels. Oh, you do need the mass of the sun, but that is on your formula sheet. Moon? Oh, how could you not want to kick a football on the moon all the way around the moon so that it hits you in the back of the head? Please. 5 is good. 6 is good. 7 is good. Imagine, let's see, that asteroid X of mass revolves around the sun with an orbit radius of 320 million kilometers. Draw 2 or more conclusions. 9 is good for astronaut Sally. 10 is good. 11 is just review. Now, I'm going to say, because we're getting into the meat and potato, 12 is nasty. I'll happily talk about it next class. 13 is nasty if you don't think about it the right way. I'll happily talk about it next class as well.